Today I want to talk about taking samples from the truncated normal distribution. This is going to be useful for the probe it code that you're going to do, and also could be useful for the load it. The same principles apply to that case as well. So let's think about a normal distribution first. Simplest case, taking draws from some truncated part of this distribution where we have some truncation region marked by A, and your mean of your distribution is here. If you have there's many different cases here. There's the case where A is over here, and you have a normal distribution that looks like this. Your mean is here. Obviously, drawing from the positive region is not going to be a problem because draws out in this tail, they don't occur very often. There's the case that I drew down here already. Let's say A is right here. Now, getting draws from this region could happen just by simulating draws from a random normal distribution with this mean and variance. It could happen, quite easily because there's lots of possibilities. There's lots of probability that the draw will be in here. There's also this possibility, though. Okay, just a more extreme version of the case below. What if your A is out here? This will never really happen. You would have to wait a long time to get a draw. If you were going to simulate from the normal distribution and only accept the ones that were in the region you wanted, you would have to wait a very long time, and the code would slow down. So what I'm going to show you is how to produce draws from the region that you want automatically without having to wait any time. This will work for most cases as long as A is within 5 standard deviations from mean. So this method will work as long as the inverse CDF is defined. You can find, if you take inverse CDF as something that's about 8 standard deviations away, you'll see that you get something that's basically just 1 or 0. Doesn't distinguish very well from 1 or 0, when actually there could be a difference. There's other methods for taking draws from truncated distributions. When the cut point is more than 5 to 8 standard deviations away, probably 5 is where you should stop. Trying to use the inverse CDF method, which is what I'm going to show you, because it just does not get good draws. It doesn't work that well. You'll get some numerical error. So the idea here is, if you have a lower cut point A, is to take x's that are greater than A only. Alright, so like I said, this is called the inverse CDF method. So you need to think about first the CDF of the truncated normal distribution, which is the one that you want now. The CDF of that distribution, let's say we get some random x that's here on this side of the distribution where we want, and we have some mean, and we have cut point A, all like this. So this is what we're going to do. Let's say that sigma equals, let's just leave sigma equal to sigma. Let's standardize everything. Okay, that way we can use the standard normal distribution as opposed to some other normal distribution. Alright, this is what you get. What's the probability that x is here? The probability of x being there in this distribution is this. You need to take away this phi of alpha because you cannot have, this distribution is only defined when x is greater than alpha. So the phi sign gives you the integral of negative infinity up to x. Okay, but our negative infinity should be replaced by a, but that's what phi of x equals. So we cannot use this unadjusted phi of x. We need to make an adjustment by subtracting off this lower end of the distribution. So we have an x here, and regular phi of x calculates all of this for us, but we need to subtract off all of this part and just consider what's greater. Okay, so this is like the ghost part of the distribution. And this is the part that we want or are interested in. Okay, so you need to subtract the 2 and then divide by only the region that we're considering, 1 minus phi, which is this part. Okay, maybe you're wondering why 1 there. That's because there's no restriction on the right side going to the right of this distribution, and the integral up to infinity would be 1. So you can just write a 1 there. Alpha is the region where you're truncating. Okay, so we can take random draws of this distribution because we know what this is, what the boundary limits of this PDF are going to be. They're going to be uniform. So we can simulate from the uniform. We'll get a number between 0 and 1, and a CDF is always between 0 and 1. And then solve for this. Well, no, let's do this. Okay. And then solve for this. The goal is to solve for x, our random number, from a truncated normal distribution. Then do the inverse normal, which is why this is called the inverse CDF method. There. And this is the formula that we use when we code it. So in the next video, I will code up a sampler